Okay, so we're going to take a look at the last part of this section, and we've been able to find Laplace transforms. We've been able to use that first translation theorem, but we haven't been able to go backwards yet. And so this is probably the most challenging aspect of being able to work with Laplace transforms is the inverses, just like with most mathematical operations. And so let's just take a look at some of the techniques to be able to find the inverse Laplace transform for each of the functions. So these have already been through the process of the transform, now they're in S, and what we'd like to do is get them back into T. So we have this f at s is equal to 1 over s to the fourth. Okay, a seemingly easy example. Now, remember we had this. We had that if we had t to the n, that was equal to n factorial over s to the n plus 1. And this is what we have. And what we'd like to do is to go backwards and put it into that form. So clearly right here, we know that n plus 1 is going to be equal to 4. Or in other words, n is equal to 3. All right, so again, I'm just looking at this. I notice that this exponent, or that has to match up with the denominator of 1 over s to the fourth, has to match up with s to the n plus 1. But we don't have n factorial. So here's what we're going to do with this. We are going to rewrite this, and we're going to say 1 over s to the fourth is the same thing as 1 over the s to the fourth times 3 factorial over 3 factorial. Right? And then what we can do is we can just rewrite this. We can factor out a 1 over 3 factorial and be able to get to our answer. Right? So sometimes we have to be sneaky with this and kind of multiply, and we have to bully it a little bit to get what we want out of this. All right? So for our inverse Laplace, we're going to say 1 over 3 factorial, so this is the denominator, inverse Laplace of 3 fact over s to the fourth. All right? And then finally, we just use the we just go backwards. We know that n is 3 in this case, so really this is going to be 1 over 6th, or 1 sixth, excuse me, t cubed. Of course, if you don't believe me, what you can do is you can find the Laplace of that. All right. In fact, Laplace of, we can just say 1/6 Laplace of t cubed is going to be equal to 1/6 times 3 factorial over s to the 3 plus 1. We know 3 factorial is 6, so this is 1 over s to the fourth, which is what we started with. So that might be a way for you to check your answer, is to just go through, once you're done with the inverse Laplace, to find the Laplace transform. A second example, 1 minus s quantity cubed over s to the fourth. As you can imagine, what we're going to do is we're going to expand this. All right, so another way to write f at s is going to be 1 minus 3s plus 3s squared minus s cubed over s to the fourth. All right, so all we did was we just multiplied it out. If you don't trust me with my multiplication, just rewrite 1 minus s cubed as 1 minus s, 1 minus s, 1 minus s. Now we're going to break it up into 4 smaller fractions. So this is going to be 1 over s to the fourth minus 3 over s cubed plus 3 over s squared minus 1 over s. And now we're just going to take the inverse Laplace of each of those. All right. Now again, we might have to be sneaky and we might have to multiply the top and the bottom by something to make it work. So all of these are the polynomial rule except for the last two. All right. Now we know that the Laplace of t is equal to 1 over s squared. And we know that the Laplace of 1 is equal to 1 over s. So, and we already have the power rule, the general power rule, t to the n is equal to n fact s over n plus 1. So we're going to use all 3 of those, but we do have to make sure that we're set up nicely with the coefficients. So let's just do them one at a time. If we want to do the inverse Laplace of 1 over s to the fourth, we already know what that's going to be, right? We have to multiply by 3 fact over 3 fact. and that's going to give us the inverse Laplace 1 over 3 fact of 3 fact over s to the fourth, or in other words, that's going to be 1/6 t cubed. We just saw that, not a big deal. For our second term, we have negative 3 over s cubed, right? Now clearly n is going to be equal to 2 for this one. Right? So right here we know that n is 2, right? And that means that the numerator has to have a 2 factorial in it. All right, so another way we can write this is we could just multiply the top and the bottom by 2 fact over 2 fact, and we can just go ahead and factor the denominator of the 2 fact, and then the 3 out, as well as the negative, so we get negative 3 over 2 fact inverse Laplace of 2 fact over s cubed. And we've actually seen this one a number of times. In fact, this was the very first one that we proved. This is going to be minus 3/2 t squared, right? And remember, that's because n is equal to 2. Over here, n was equal to 3. All right, so let's hold on to these. So we need this, and we need this as part of the sum. We have 3 over s squared. That one's really easy because we can just factor the 3 off. So we have 3 Laplace of 1 over s squared, which is just going to be 3t. We're going to hold on to this one. And then finally, we have the opposite of the Laplace of 1 over s, which is just negative 1. Right? And again, I'm just using these two rules right here to get those. And so our final answer, the inverse Laplace, and this one should be an L minus 1, this one should be an L minus 1, inverse Laplace of 1 minus s cubed over s to the fourth. We're just going to juxtapose this and make it a sum. So that's going to be 1/6 t cubed minus 3/2 t squared plus 3t minus 1. All right. So hopefully that makes sense for those first two examples. Not meant to be too difficult, but it does require a pretty good knowledge of all the fundamental Laplace transforms. Right? This one's not too bad. So we have a 5s cubed plus 3, right? Or s squared plus 3, excuse me. And what we have to do is we have to think of something that it's close to. And this kind of looks like it might fit the form k s squared plus k squared. Right? So we're going to cheat again, and we're going to rewrite this function in preparation to take the inverse Laplace. 5 times 1 over s squared plus 3, and we know that k in this case is going to be equal to not 3, but the square root of 3, right? Because k squared is equal to 3. Right? So what we're going to do is we're going to multiply the top and the bottom by square root of 3 over square root of 3. We're going to factor out the 5 and the root 3 in the denominator, and we're going to say 5 over root 3 inverse Laplace of root 3 over s squared plus 3. Right? And remember, this is equal to the sine of kt. And so finally we can write this as 5 over the square root of 3 sine of root 3, excuse me, t. In fact, let me write this as t roots of 3, so that way we understand that the t is not under the radical. Right? So pretty cool that we can try to just do a little bit of algebraic manipulation with this and be able to get to our solution. All right. This one looks like it's going to be really tough, but it's actually going to be one of those translation theorems. Okay, so, and remember I wrote out the translation theorems, and when I was doing it, most of you were probably thinking, okay, just get to the point. Well, I did it because that way we can see the translation going on. Because what we can do is we can rewrite this as 1 over s to the 5th power as s approaches s minus 3. Because clearly this can be written as s minus a minus 3. Right? And in this case, a would be equal to minus 3. Right? So hopefully that makes sense as we're going through this. Actually, it would be s plus 3, which means that a is going to be equal to negative 3 when we do this. Right? And so when we get our answer, we could think of this as the inverse Laplace of 1 over s to the 5th power as s approaches s plus 3. Now we're going to have to do two things. First of all, we're going to have to doctor this up a little bit to be able to get the right number. All right. Clearly, in this case, the exponent n. So remember, it's going to be n plus 1. In this case, n is going to be equal to 4. All right. It's always 1 less than whatever s is. If you don't believe me, just go look at some of the previous problems. The other thing that we have to do is we have to be concerned as to what this means. All right. But we'll get there. We're going to multiply. So let's just set this up. So L minus 1, 1 over s to the 5th times 4 fact over 4 fact, right? Because we need to make sure that the numerator has a 4 factorial in it. S approaches s plus 3. And as by our first translation theorem, we can be done with this. So this is going to be equal to t to the 4th power, 1 over 4 factorial, right? So we just pull out that 1 over 4 factorial. And that's this right here. These two just are going to turn into t to the 4th power. And what happens with this s approaches s plus 3? Well, that's our first translation theorem. All right? And that's going to be e to the minus at, right? Where in this case, I'm sorry, e to the at, where in this case a is negative 3. And so this is going to be e to the minus 3t. And this is our inverse Laplace. All right. Clearly, we could simplify this into 1 over 24 t to the 4th, e to the minus 3t. All right. So hopefully this is helpful for you to see some of the techniques thus far. And we're not really doing anything too difficult. Okay. All of it is just a little bit of algebra and using all of the rules that we've seen so far. All right. Now, there is going to be a little bit more intensive algebra as we go along. So in the next set of videos, what we're going to do is we're going to take a look at some of the more, even more common techniques, but they are a little bit more rigorous to find our inverse Laplace transforms.